Hello everyone, we're still in section 4.4, which is the mean value theorem. This is problem 157. I'll go ahead and write out what the problem is. So our function is 3x cubed plus 2x plus 1. And the interval in question is from -1 to 1. And here over on the right hand side, I've actually got the function graphed. The scales from -1 to 1, and the vertical scales from -6 to 6. And notice it's continuous, definitely differentiable because it is a polynomial. And the right endpoint is 1, 6, and the left endpoint is -1, -5. So I'll just label those. How about x1, y1 is the left endpoint. And x2, y2 is the right endpoint. And if I draw, a rough sketch over here on the right hand side, and let's just say looks something like this, and then it does something like that. Of course, this is just a sketch. There's one endpoint, and over here, of course, is the other endpoint. And we attempt to draw a nice line connecting the two endpoints. And if I can get my graph paper back over to the side here, sorry about that. And so I'll draw a line connecting these two, something like that. And notice that that blue line has its own slope. Okay, and so potentially there may be more than one spot where the slope of the secant line, which is in blue, is the same value as the derivative. So let's try to see, maybe right here they have the same slope, and maybe over here. Okay, what I'm looking at here is somewhere in here they have the same slope, and over here they have the same slope. So the mean value theorem guarantees at least one value c in the open interval from -1 to 1, where the derivative, meaning the slope of the red trace, is the same thing as the slope as the secant line in blue. So we're guaranteed one. There might be more than one. Okay, so let's go ahead and try to find what values of c in the open interval -1 to 1. So the mean value theorem guarantees there's a c, at least one c, in the open interval -1 to 1, where the derivative at c, sorry about that, where the derivative at c what is going on here? Come on now. Fighting with something here. Okay, so this is going to be the same thing as the slope from x1, y1 to x2, y2, and that's going to be y2 minus y1 for x2 minus x1. So we're guaranteed one spot between -1 to 1 where the slope is the same thing as the slope of the secant line. So let's see what that slope has to be. and it's going to be 11 halves, or 5.5. So somewhere in the interval -1 to 1, the derivative goes to a value of 5.5 or 11 halves. So let's first figure out what the derivative is. Of course, we just use the power rule on the polynomial. And we get 9x squared plus 2. So we'll set that to 5.5 and solve. And again, I don't know what's going on here. Then I'd fix this problem with the cursor doing this. Okay, let's try this again. We want this to be 11 halves. So I'll subtract 2 from both sides. So 9x squared will be 7/4. I'll divide by 9. And then apply the square root. So it's going to be plus or minus the square root of 7 over 6. So the square root of 7 is somewhere between 2 and 3. So we're looking at a little bit bigger than 1/3 and a little bit less than -1/3. And so we have two c values. So c could be equal to minus root 7 over 6 or positive root 7 over 6. And that finally completes 157. So notice here there's one spot over here at something a little bit bigger than 1/3, and somewhere over here a little bit less than -1/3.